Okay, so let me put on the recording. Thank you. Good morning. Good morning. If we look at the tables, right? So what do we have covered yesterday, right? There's of course there's one row that I was asking you guys to do, which is to summarize which one of these functions are, you know, one-to-one functions, right? I hope you have done that. The next thing I like to address is that mistake I made on the quiz. Okay, so let me bring up the the quiz page. Okay, I made a very bad mistake, and I also want you guys to understand and you know, how bad that mistake was. Okay, and so you don't make the mistake again. Well, I should not make that mistake, but I also want to make sure you get your credit. So I will talk about how I will compensate you for that mistake. So that's on quiz number 3. Okay, so let me share the screen. Quiz number 3. Okay, on this quiz, if you look at the last question. Okay, if you look at the last question primarily summarizes the, you know, I have already corrected. I have corrected the mistake. The original question, it didn't have the cubic root. And I overlooked that. I basically clicked the wrong button when I did the typesetting. Okay, so this quiz, this question is on the recording. It's on the recording we did last Thursday. So the first one is correct. Okay. The absolute value of a positive number is the same as the number. If you think about taking absolute value of 1, absolute value of 3, absolute value of 5, all of these are positive numbers being taken absolute value, which is where, you know, we have addressed this issue in that recording. So this first one is a correct one. Number B, the absolute value of a number, of a negative number, is its opposite. So that's correct as well. And C, the absolute value of 0 is 0, right? Everybody agrees with that. D, okay. D, we understand that's a mistake, right? That's a mistake. And we also know what's the right answer. It's a missing absolute value, right? Missing absolute value. E, okay, as it is now, it is correct. But what it was on the quiz is that the cubic root was replaced by the square root. You guys probably remember that question, right? So for that reason, so when I was making it, I thought this is the question intended, and I type it in, but I just don't see that mistake at the time. I don't see that mistake at the time. So the correct answer should be A, B, C, E. Okay. However, some of you, because as it was the question before the correction, the correct answer would have been A, B, C. You guys follow me? So that's why I sent you guys that message yesterday. This is a correct. Okay, this is a correct. But without that cubic root, it's wrong. Okay, without cubic root, that's wrong. So that's my correction, because this quiz is worth 4 points. It's worth 4 points. Therefore, I have looked at the grades, and some of you actually got all the points. Okay, so you probably have chosen A, B, C, E. If you, for whatever reason, if you already have 10, then I probably would not add more points to you. But you need to understand there's a typo there. You need to understand there's a typo there. For those of you who got lower than 10, I will add a maximum of 4 points to your grades manually. Is that clear? Is that clear, everybody?
Yeah.
Okay.
Yes.
So once again, I apologize for the mistake, but we also want you to understand that these are commonly used results. So we want to make sure you get it right, okay, and not be infected by my mistake. All right, so let's move forward. Let's move forward. Okay, let's go back to this page. And today, okay, so if we look at what we have done, right? We have been working with these 8 functions in basic one, right? And we have covered domain, range, right? The first 8 functions. Okay, we covered domain, range, intercepts, right? And the graph, which is the image. Graph is the image. Sometimes, an output is called a image, right? We saw that word being used. And today, we are also going to look at another thing, okay? Continue with the concept, the study of concept. And then we're going to continue to study these other functions, okay? The other 2 concepts we're going to study today, one is called increasing function, and the other one is called decreasing function. So yesterday, we spent quite a lot of time to study what is one-to-one function. How do we make the argument to say a certain function is one-to-one or a certain function is not one-to-one? Okay, so and today we're going to introduce the concept of increasing function. So please write it down if you haven't done so on your flashcard, and the decreasing function. Okay, so we're going to explain the meaning. Even though increasing function, decreasing function is something we have seen before, but these 2 concepts will be extensively used in chapter 4 of calculus 1, okay? And of course, this concept will be introduced again, but we will see these functions as we study these, these basic functions. Some of them are increasing, some of them are decreasing. So let's look at the definition, okay? Because we just studied one-to-one function, okay? Because we just studied one-to-one function. So it's going to be fairly straightforward to look at the definition. And I thought it would be a good training for you to study this definition right here and right now. Okay, so so this time is whenever. Okay, so please write down these 2 definitions. And look at the wording. I want you guys to look at the wording, okay? And I also would like you guys to tell me, in comparison with one-to-one function, okay, what differences do you see here? What differences we see here? What do they mean? Okay, so this is how you study those concepts in calculus. You can't just read it and move on. You have to think about what did it mean, and you look at the examples and what it means, right? To gain better understanding. So we also address this issue of the method of study. So now a function is called an increasing function. Okay, I should put a word here. Okay, on an interval I, on an interval I, if, okay, and once again, so in comparison with the definition of one-to-one function has to be on the entire domain, right? Did you guys see that? One-to-one function has to be on an entire domain, but the increasing function, however, is on a specific interval, Okay, so let's see what it says. Okay, look at increasing. Increasing function, of course, we know that we started with a function. We start with a function. So this is already a function. It's already a function. What does it mean? It's already a function. We have input, right? And this rule of the function f produces an output, and that output is called f of x, right? So input output, you see, input output, the rule is set, And then whether a function is increasing or decreasing, we often address just on an interval. An interval usually is it's smaller than the domain. It's smaller than the domain, right? For example, just a part of in the domain. And in that particular interval, whenever one input is smaller than the other, and their respective input, the output will also have the same relationship. So this is whenever. Okay, so we can also figure out, the to be and not to be. Okay, did you guys write it down? Okay, so what it means. Take an example. Okay, take an example. I'm going to take this example. Well, maybe this one, right? Example. Ex. Okay, a function which you could call f of x equals to absolute value of x. And the domain of this function is, what's the domain here? All real numbers, right? So you guys all know that. All real numbers. But if we look at part of the curve, okay, on the interval between 0 to infinity, if we look at this interval, okay, whenever x1 is less than x2, okay, the input. So let's look at the, let's understand what is, suppose I have an x1 here. Okay, so I'm using red for the, that's fine. I'm using red for the input. Okay, so this is x1, right? And I will have another input, which I'm going to call it x2, x sub 2, right? You see, the input is measured from the origin horizontally. The output is measured from the origin vertically. Did you guys write it down, that statement? And this concept, as trivial as it is crucial, because that's the ground rule. Okay, that's the ground rule. I'm going to write it down for you. Okay, I'm going to write it down for you just in a minute. Okay, so first I'm going to do the demonstration. So this is the x2. Okay, this is x2. And of course, this point is x1, and this point is x2, right? Input x1 and input x2. x2 is smaller than x2, right? x1 is smaller than x2. And their respective output, if you understand the basic principle, right? And the output 1, and that's the output 2. So the green one, this is f of x1. And this is f of x2. Okay. Do you see that x1 well?
Yes, Professor.
Okay, thank you. Okay, so this is x1. Okay, so you can see, and this has to be true whenever. meaning it has to be true always. Okay, it has to always be true. Okay, so that's what it means. So let's describe it. What's the description of it? The description of it is whenever x1 is less than x2, which is the input, one is smaller than the other, and their respective output also bear the same relationship. So that's what it means. For example, in this case, what would you say? What would we say about the increasing, decreasing? We used to just, we can tell from the curve, if it goes up, we say increasing, if it goes down, we say it's decreasing. But as we advance in mathematics, we need to concisely describe the situation precisely, right? And that language is increasing function. And the interval in consideration here is from 0 to positive infinity. So in words, this is how we describe, okay, in words. In the interval, okay, from 0 to infinity, whenever, you can switch the order. Whenever x1 is less than x2, because I already mentioned this interval, therefore I don't need to mention this again. Okay, f of x1 is less than f of x2. In particular, if we apply the function and you write x1, x sub 1, and here is going to be x sub 2. Right? That's it. Then we say this function is increasing on that interval. So that's the language you use. That's how we say it. Now let's look at decreasing. Right? So decreasing would be similar, right? Decreasing would be similar, but decreasing is reversed. Okay, decreasing would be reversed. So let's look at, it's obvious the decreasing is on the other side, right? Decreasing is on the other side. So let's look at the situation on the other side. So I'm going to clean this up and look at the decreasing situation. So this time, I'm still going to use red for the input, right? So I'm going to have two input. So for the decreasing description, okay, for the description of decreasing, okay, so what do we have here? Is that we have x1, we still have x1 less than x2. But in this particular case, right? For example, this is going to be my x1. Right? And my x2. So once again, all the inputs are horizontal measurement from the origin. All the outputs are the vertical measurement from the origin. So the origin is a point of reference, right? If you guys study physics, you will know that there's a point of reference, right? In mathematics, we use that point of reference. Our point of reference is origin. And in real life, of course, you set your own points of reference. But the input output, in this case, even though you see x1, I'm sorry, I should reverse the order, because right here, this should be x2, this should be x1. My bad, okay? Because this is x1, this is x2. You guys see that? Why is that? Because they're all negative, right? They're negative. In this case, x1 is less than x2. Do you guys see that? You may say, hey, x1 is longer. True, x1 is longer, but it's a negative. Do you follow me?
Comparing on the number line, yes.
On the number line, so this number, which is x2, is larger than this number, yes? The number on the right is larger than the number on the left.
Agreed.
You follow me?
Yes.
Everybody else?
Yes.
We still follow that whenever x1 is less than x2, and what are their respective output? Their respective output for x2 is this guy, and for x1 is this guy. You guys see that? So we're gonna mark it, okay? So these are the notations we also need to get used to. F of x1. And this guy is f of x2. Okay, let me see if I can write it here. F of x2. You follow me? Now, is that a statement true under the circumstances?
I'm sorry, could you repeat that? I didn't really hear you.
Whenever x1 is less than x2, do we have a situation x1 is less than x2? This is x1 and that is x2. Measurement horizontally from the origin.
Yeah, x1 is less, yeah.
Right, even though x1 is longer, but they're on the negative side of the number line, right? So the interval in our consideration, what is the interval in our consideration? Is from -infinity to 0. Okay, be patient with me. We're learning how to use this language. Okay, the situation is simple enough, but we have to learn how to use the language. Okay, now whenever x1 is less than x2 in this particular interval, right? Because when we talk about increasing, decreasing, it's all about using the interval. Okay, the interval doesn't have to be the entire domain. It can be the domain. Okay, but it doesn't have to be. It can be smaller than the domain. So whenever x1 is less than x2, f of x1, this is the f of x1, the taller one, right? Because when we take absolute value on both sides, what happens? Okay, I'm gonna give you a little cheat sheet. Okay, you don't put this on your argument for paper you turn in, but in your mind, you can think out loud. Think out loud, right? -5 is less than -2, right? But if we take absolute value on both sides, if we take absolute value of -5, and then we take absolute value of -2, which one would be larger?
The -5 or aka +5.
That's right. It's going to be reversed, right? Do you follow me?
Yes.
So we are considering a general description. When both are negative number, okay, one is smaller than the other. After we take absolute value, the absolute value of x sub 1 is going to be larger than the absolute value of x sub 2. This is the application of the definition of a decreasing function. This piece, don't put this piece ever turn on the paper you need to turn in. Don't. Your teacher doesn't need to see this. You just need to, this is like a little hint, okay? But this is just an example. One anecdote does not reflect the general situation So don't use this, don't put it on your paper, but use this as observation point. Do you guys follow me? So on the paper I will turn in, I will just write this down. But in my mind, I went through many numbers. In my mind, I went through many numbers as such. And this statement, well, we going through all those numbers in our mind is just to ensure that this statement is true. Now the question is, do you agree this statement is true? So I'm making a statement here. Everybody?
Oh yeah, no, I agree. Never mind, I agree. It's absolute value.
Do you agree?
X1
Is that
better
true?
than
Because
X2. Yeah.
because you need to make that judgment call before you turn in that paper, whatever you do. And your teacher will do likewise. Because for me, if I see your paper, if I see your work right now, I would say, is that statement true? So I will be going through, I'll be thinking about their counterexamples and so on and so forth. I need to guarantee when I give you those credit and the statement you make here must be completely true. Okay, I'm going to explain to you why you don't write those anecdotes just in a minute. Okay, so by this time, then you can say, and the way we write it this way is because the definition is written that way. So we kind of quote it, right? Do you see that we're quoting that definition, but we're not completely quoting that definition because we added the function we are considering in that specific situation. You follow me? And this is something you're going to do all the time in Cal. Okay, whether you say something has limits, something doesn't have limits, something is continuous, something is not continuous, differentiable, not differentiable. In all of these cases, it's going to be similar to the situation here. Okay, that's how we learn this language, how to make this statement, how the grammar works, right? So in the definition, there's whenever. You may like to use whenever. Of course, whenever may not be the only words you use. You can also use these words. You can say for any. Okay, that's another for any x1 less than x2, and in that particular interval, and the absolute value of x1 is larger than absolute value of x2. You can use these words, but that's pretty much it. That's pretty much it. Whatever other phrases you create. Or you can say for arbitrarily chosen input x1, x2 from the interval negative infinity to 0. You can create these sentences along the same line, but they all reflect the same meaning, which is whenever x1 is less than x2. And you have to specify the interval, because whenever you indicate input, you have to tell the reader where they're from. You have to tell the reader where they're from. Okay, so for any, so that's about, what you can do. And then you can draw the conclusion. You say thus, the function, right? The function, I'm just gonna copy and paste and change, is a decreasing function on the interval from negative infinity to 0. Okay, so this will be the same wording. Similar wording you can use. So could you please write that down? You guys get the hang of it? We're using this language, right? We're using this language. So whenever is the key. Okay, now the question is, what is the opposite of it, right? So in summary, for this particular function, we have the absolute value of x here. And you can see on part of the domain from 0 to infinity, that's increasing. On the other side of the domain from negative infinity to 0, it's decreasing. So that's how we describe increasing, decreasing. In the future, in your calculus class, you will also encounter this. As I said, it's going to be I think it's going to be in chapter 4, most likely. is that you describe the maximum minimum, then you say, okay, on this interval it's increasing and then it's decreasing. So there's a top point. Okay, and so on and so forth. So these are the wording you're going to use, actually using them in your calculus class. Okay, so without further ado, we talk about increasing, decreasing. The next question is what's the opposite? Because I was just talk about like yesterday, whenever we have a definition telling us what is, what to be, and there's a what not to be. Okay, so what is not to be? Which is the opposite of it. So what is it to be and what's it not to be?
To be was increasing, not to be decreasing.
Is it true that if it's not increasing, it must be decreasing?
Yes.
Couldn't it just remain constant?
That's right. Good thinking. It's not necessarily true because you can see constant function is neither increasing nor decreasing. So we have a situation that the function is neither increasing nor decreasing. Right? Do you see that?
Yeah.
It's neither. Now let's look at this one. Right? Let's look at these 8 functions, right? Using the definition we talk about. Because in this case, how do you say it's not increasing? How do you say it's not decreasing either? It's neither. Very good thinking. Constant function is a very good example. It's a very good example. Because for any 2 input, right? Increasing means that one input less than the other, and the output will have to be having the same relationship. One is less than the other. And for constant function, that's certainly not true. They're neither less than or greater than. They're equal to, right? So not increasing does not mean it is decreasing, vice versa. So let's write down that statement. Let's write down that statement. Okay, very important, okay? Because in this, you're gonna start to make a statement and generalize or not, okay? So every word you put in together, you have to be very careful. If a function is not increasing, it does not necessarily, did I write down that word correctly? Necessarily, the 2L, decreasing. An example, the constant function. Okay, the constant function. This function is neither increasing nor decreasing. Okay, very good. You guys are thinking. You guys are thinking. I have next question. What's the relationship between one-to-one function and the increasing function, decreasing function?
I'm sorry, could you repeat that? I didn't really hear you.
Yeah. If a function is increasing, okay, if I'm giving you an increasing function, is this function one-to-one? If a function is increasing or decreasing, or I'm going to make it a separate, 2 separate sentences. Is this function one-to-one?
Wouldn't it depend on the interval?
I'm sorry?
Wouldn't it depend on the interval that like
That's
we're
right.
looking at?
That's right. But suppose you have the same interval and it's increasing. Doesn't mean it's one-to-one. So how do we examine this situation? This usually will require rigorous proof. Okay, but the proof will be pretty straightforward here because whenever, okay, you have when we try to prove this, you may like to put these definitions together. We want to put these definitions together. Okay, so now let's do this. I'm going to show you how to do it. Okay, increasing function. And what's the definition of one-to-one function?
But
What's the
there's
definition of
one,
one-to-one function?
there's
We did
one
the last
output
one.
for every
Sorry?
input. There's one output for every input.
That's right. Whenever the inputs are different, their outputs are different also. Okay, so this is one-to-one function. Okay, so this is going to be serious reasoning. Okay, this is going to be serious reasoning. So this is one-to-one function. Increasing function. Okay, so my question is, if it is increasing, is it for sure to be one-to-one? Okay, and the next thing to consider is vice versa. Vice versa. These are the questions you often face in calculus classes, calculus thinking. Okay, whether it's a limit concept or continuity concept or differentiability concept or other future concepts. Okay, so now, if it is a increasing function, right? So if it is an increasing function, if function f is an increasing function, what does it mean? Definition of increasing function applies, right? The definition of increasing function applies. Yes? So how do we demonstrate it might be one-to-one or not? So we're gonna work towards, or not to, if you have counterexamples, right? So I will start with whenever, right? Because the increasing function would be on an interval, right? I would say on the interval. On an interval I. Okay, and of course, one-to-one function is on the entire domain, but if it works for interval on interval I, certainly it should, I is part of the domain, right? I is part of the domain. Now, because the wording in one-to-one function requires whenever, right? Whenever. So whenever, oh wait, this is an increasing function, I'm sorry. So we're gonna use whenever on the interval. So whenever x1 is it's not equals x2 in the interval I, right? Because if it is true on the domain, it should be true on the interval I, right? Because I is a part of the domain, right? Okay, so whenever x1 is not equals to x2, because x1 is less than x2, right? So one must be smaller than the other because they're not the same. Suppose, say, x1 is less than x2. Right? Because they're not the same, so I can assume one is smaller than the other. Then f of x1 is going to be less than f of x2, x sub 2. Because it is an increasing function. That's what increasing function tells us, right? If this is true, then this is true. And if one output is less than the other, that means they're not the same. That is, one is less than the other, that means one is not the same as the other. Thus, this function is 1-to-1 on interval I. Then you could say, oh, what if x1 is greater than x2? Well, if x1 is greater than x2 because it's increasing, then f of x1 is larger than f of x2. Okay, so I'm giving you a glimpse of the thinking in calculus, even though not for the same concept in calculus, but this is basically the methodology of thinking. For decreasing function, you can make similar argument, but I'm not going to spend too much time here. I vision some of you may have hardship with this, but if you have time, just watch this over and over and come back to me with your questions, okay? Because these thinking, this how to say the words, it really requires and demands a lot of attention in order to gain the better understanding, okay? Therefore, this is a yes. Okay, if a function is increasing on an interval, then the function is 1-to-1 on the interval. So the only thing I need to add is I'm going to add, say, on a specific interval. But is it reversal true? That's another question. In calculus class, you often ask these questions, right? What if the conclusion becomes a condition, and the condition becomes a conclusion? Will that still be true? Okay, so in this case, okay, in what we just studied, right? We have just demonstrated, right? If a function is increasing, right? And it is surely 1-to-1. Okay, so increasing is 1-to-1. If it's increasing, it's 1-to-1. But what does it mean by vice versa? If it's 1-to-1, is it increasing or decreasing?
Wait, I don't really understand the question. Can you repeat
Okay,
it?
the next question is, I'm going to reverse it, right? So on this piece, we have demonstrated, okay, if a function is increasing, then it is a 1-to-1 function on the same interval, right? We have proved it.
Yeah.
But what if I switch the conclusion, right? I give a given a function is 1-to-1. If a function is 1-to-1, is this function increasing or decreasing? You see, it's reversed. In this case, this is the condition, that's the conclusion, right? Do you follow me?
Yeah.
You guys follow me? This side is the condition. And that is the conclusion. Now I reverse the conclusion and the condition, which turn into this. So now conclusion becomes condition. Will the reversal be true?
So just to be sure, you're saying if a function is 1-to-1 in the interval, you're asking.
If
if
it
it's
were 1-to-1, isn't necessarily increasing or decreasing. And first of all, it's going to be on the domain, right? Because 1-to-1 concept is going to be on the domain.
Yeah.
But it doesn't mean the function is going to be increasing or decreasing.
Is it the same interval of that x1 is less than x2?
Suppose we should just talk about domain. We just talk about domain. Is this function increasing or decreasing on domain?
Professor, for the first part, a function is increasing, then this function is 1-to-1,
Right.
condition, conclusion. Can we have an example like f of x equals x cubed? Then that is increasing function at the same time it's 1-to-1. So we have visualization of the first rule.
Well, you give an example,
Yes,
right? You have given an example. It is increasing and it's also 1-to-1, right?
yes,
But this example cannot represent all of the functions,
that is correct. That is correct.
right? It cannot represent all of the functions. And this goes back to something I promise you I will go over, is that, for example, we often see the advertisement on TV, right? You see a nice lady will get on TV and tell the audience, I'm taking this Lunesta, something like that. Then my insomnia is gone. Right? My insomnia is gone because I've taken Lunesta. Can you conclude that Lunesta is going to heal insomnia for everybody with insomnia?
What I meant was a example for each part. Maybe visualization help us to understand the question and answer your question for the second part, which we might have another example for the question right now you are asking. Is it decreasing function? If a function is 1-to-1, therefore, is the function is increasing or decreasing? It can be decreasing too. And 1-to-1. Like
there are functions that are increasing and 1-to-1. The question is, if it's 1-to-1, isn't necessarily be increasing or decreasing.
Oh, okay.
Do you understand? I think so. Let's go back to the
Condition.
question of anecdotes, right? I was saying that you use the example of x raised to the power 3, and that function is increasing and 1-to-1. That's true. But you cannot take this anecdote. So this lady takes the Lunesta and her insomnia is cured. You cannot infer, you cannot draw the general conclusion that all the other functions will bear, all the other functions that are 1-to-1 is also going to be increasing or decreasing. So we need a more rigorous proof than using one example. That's my point.
Yes.
So we understand you cannot use, say, one lady, I take the Lunesta and I can sleep well, and I cannot say, oh, Lunesta is going to work for everyone with insomnia. Does that make sense?
Yes, yes.
So that's why I was telling you, don't use those examples to prove to be, because those are just anecdotes. That lady on TV, and she was telling us that Lunesta works for her, is just one anecdote. And the anecdotes cannot be used as a proof. Okay, so now this is the condition. Okay, can we say the function is going to be increasing or decreasing? Okay, I want you guys to think about this. Okay, because I don't intend to spend a lot of time here because I might lose a lot of you. So I'm trying to give you a taste of calculus in terms of methodology study. Okay, but I'm going to leave this question here for you to think, to sort it out. Okay, it's not going to affect your grading anyway. It's just like those, the kind of material for thoughts, reflect the methodology and a lot of the methods we use in calculus classes. Okay, condition, conclusion, you switch the condition and conclusion, is that still true? All these examinations and the related proof. And so I don't intend to spend a whole lot of time here. So to next, we have the basic concept of increasing and decreasing, and we did not go in details to do the to be or not to be, right? If you want to do it, you want to discuss this with me, I will be happy to spend time with you to discuss. But for this course specific, and I'm going to continue on something we must do to prepare you for a calculus class, which is the next functions, number 9. Okay, so let's roll up our sleeve. Okay, back to basic 1. Okay, number 9 is y equals to 2 to the power x. By this time, I assume everybody have done this. But it might be like many years ago, or last semester. So let's revisit this function. And of course, we still consider graph, domain, intercepts, right? Anybody can tell me something about this function? First of all, the rule, right? Let's look at the rule. The rule says, well, whatever input you give me, I'm going to take your input to power 2. And I'm going to produce an output. So that output is going to be 2 to the power x. You see, that's the input output. That's how it's been produced. Right? That's how it's being produced. So then naturally we'll be thinking about domain. So what number will be qualified for input, and what will be the consequence? What will be the consequence of the domain, which is make the range? Hello, everyone. Anybody?
I would be the last to answer, Professor. Is that correct?
Yeah, maybe you want to wait a little. Should I call out some names?
Are we, do you want us to give you an example? I'm sorry, I didn't really I wasn't following. I was writing.
You can give me an example, but mainly we want to know what are all the possible numbers that are qualified to be the domain, such that for each of those numbers, it will produce exactly one output. Definition needs to fit definition, right? Definition of function means for each input in the domain produces exactly one output in the range, right? So we want to figure out what number will be qualified for input. What number will be qualified for the input?
I'm not really sure.
Okay. Let me give you some numbers. Okay. Let me give you some numbers. Input. Output. Everybody, please have your paper pencil with you. Okay, input. I'm gonna give you in the input -3. Would that qualify? -2. Of course, I can give you decimal fractions, okay? -1, 0, 1, 2, 3. Okay. I'm gonna give you a half. Just for the fun of it, so you know that it can be fraction, it can be decimal. And just put them in a proper order from smaller to larger. Could any negative number be fitting for an input? How do we
Yeah.
operate to get the output? So when the input is -3, right? 2 to the power -3. I'm making the fonts a little bit larger so you can see the negative sign. Can you see the negative sign here?
Yes.
Okay, so what is 2 to the power -3? Shall we do some review?
It's just 0.125.
Okay, we need you to be able to do this. Okay. B raised to the power of -n is equals to 1 over B to the power of n. Remember seeing something like this before? B to the power of m multiply B to the power of n is equals to
B to the power of mn, right?
B to the power of what?
mn.
Mn like this.
Yeah.
Does everybody agree with it? Okay, obviously we need some more review on these topics. Okay, let's do some more review on the topics. Okay. Review about power. Okay.
Oh wait, no, it would be m plus n, right?
Okay, so we have multiple choices. B to the power of m plus n, ym plus n, ym multiply n. Right, so let me just do a brief review for you. Okay, it's very important. I don't hear a lot of people responded. So if you guys want to say something or you private message me, is it necessary for me to do a review for you on this part? Yes or no? Okay. We understand that 2 times 2 is what?
4.
2 squared, right?
Or like that too, yeah.
And times another 2 is what? 2 to the power of 3, right? And another 2 is going to be 2 to the power of 4, right?
Yeah.
And 2 is called a base, and 4 is called exponent, right? The power.
Mhm.
2 is called the base, and 4 is called the power. And to generalize, right? We may have b times b times b times b, and that's b to the power 4. You guys follow me? That's a generalization, right?
Mhm.
It could also be, this can be generalized as well, right? If we have n terms in multiplication, we have n of them, b times b times b n times. So that will make it b to the power of n. Okay, so that's the generalization, right? That's a generalization. So after the generalization, hold on, I need to answer this phone. I'm sorry, guys. Hello?